Welcome to this gentle exploration of one of the universe's most profound and beautiful mysteries. Tonight, we drift into the quiet contemplation of black holes, those cosmic sculptors of space-time that teach us the most intimate secrets about the nature of time itself. There is something almost musical about the way these invisible giants conduct the symphony of physics around them, slowing time to an eternal waltz, stretching moments into millennia. Picture, if you will, an astronaut approaching the event horizon of a black hole. To us, watching from a safe distance, their movements become increasingly languid, as if they were swimming through cosmic honey, their gestures slow, their signals redshift into deeper and deeper frequencies until they appear to freeze completely at the threshold of forever. Yet from their perspective, time flows normally. They fall through in mere moments, unaware that to the outside universe, they have become a permanent fixture in space, preserved like an insect in amber, made of curved space-time. This is not mere science fiction poetry. This is the profound reality that Einstein's equations whispered to us over a century ago. That time is not the steady metronome we once believed it to be. Instead, time is a river that bends and pools, that rushes and stagnates, depending on the gravitational landscape through which it flows. Near a black hole, this river of time moves so slowly that what seems like seconds to a falling observer stretches into centuries. For those watching from afar, it is both humbling and beautiful that the universe chose to reveal this secret through objects so extreme, so removed from our everyday experience. Black holes are nature's most elegant demonstration that time and space are not separate entities, but aspects of a single, malleable fabric. They show us that the now we experience is deeply personal, intimately tied to where we stand in the gravitational embrace of mass and energy. In the quiet depths of space, where black holes spin their patient dance, time becomes something we can almost touch. It becomes thick, viscous, resistant to the passage of events. Every photon that struggles to escape from near the event horizon carries with it the story of time's malleability, redshifted into longer wavelengths by the effort of climbing out of time's deepest well. There is something profoundly calming about contemplating this cosmic choreography while our human lives rush by in what feels like accelerating moments. Somewhere in the universe, time itself is learning to be patient, to stretch and slow and savor each quantum of existence. The black hole, in its dark majesty, becomes a master of temporal meditation, teaching space and time to move with the rhythm of eternity. There is something almost sacred about our relationship with black holes, these invisible teachers that have shaped our understanding of reality's deepest principles. Tonight, as we settle into this gentle contemplation, we might ask ourselves, what is it about these dark sentinels that makes them so crucial to our comprehension of existence itself? When we peer into the cosmic abyss where black holes reside, we are not simply looking at exotic objects in distant space. We are gazing into mirrors that reflect the fundamental nature of time, space, causality, and information. Each black hole is a natural laboratory where the extreme physics that govern our universe are displayed with crystalline clarity, like cosmic Rosetta Stones written in the language of curved space-time. It is remarkably beautiful that these objects, defined by what they hide rather than what they reveal, have become our greatest teachers, about the visible world. A black hole shows us that space is not an empty stage where matter performs its dance, but rather a participant in that dance, bending, flexing, responding to every gravitational whisper. Time, too, sheds its mask of universality near these cosmic actors, revealing itself to be as personal and relative as a heartbeat. Through black holes, we have learned that the universe operates on principles that seem to defy our everyday intuition, yet follow mathematical laws of extraordinary elegance. They have taught us that information might be preserved in ways we never imagined, encoded perhaps on two-dimensional surfaces that describe three-dimensional volumes. A concept so beautiful, it seems like poetry written in the language of physics. As we drift deeper into this mystery, we discover that black holes have become essential characters in our ongoing story of cosmic understanding. They bridge the gap between Einstein's smooth, geometric vision of spacetime and the quantum mechanical realm, where particles flicker in and out of existence. At their event horizons, these two great pillars of modern physics meet and whisper to each other in mathematical dialects we are still learning to interpret. The importance of black holes extends beyond pure physics into the realm of philosophy and meaning. They force us to confront questions about the nature of information, the arrow of time, and the boundaries of knowledge itself. When Stephen Hawking showed us that black holes evaporate through subtle quantum processes, he revealed that even these most permanent-seeming objects are temporary residents in the universe's grand hotel, checking out so slowly that their departure spans times longer than the current age of the cosmos. Perhaps the most profound gift that black holes offer is their lesson about perspective. They show us that reality depends fundamentally on where we stand, when we observe, and how we move through space-time. The event horizon that seems so definitive to a distant observer simply does not exist for someone falling freely inward. It is a boundary that exists only in the eye of the beholder. In this gentle dance between observer and observed, black holes reveal that the universe is far stranger and more beautiful than our ancestors ever imagined. Yet it operates according to principles elegant enough that the human mind can grasp their outlines, even if their full implications remain shrouded in mystery. In the quiet countryside of Yorkshire, in the year 1783, a curious mind named John Michell was contemplating a question that would not be fully answered for more than 2 centuries. Picture, if you will, this gentle clergyman scientist sitting by candlelight, pen in hand, wondering about the behavior of light itself. What would happen, he mused, if a star became so massive that light could no longer escape its gravitational embrace? There is something almost musical about how scientific ideas gestate across centuries. Michel's thoughts about dark stars were like seeds planted in the fertile soil of human curiosity, waiting for the right conditions to bloom into full understanding. He had calculated, using Newton's laws and his own intuitive leaps, that if a star possessed enough mass packed into a small enough volume, its escape velocity would exceed the speed of light. Such an object would be invisible, he reasoned, a cosmic ghost, detectable only by its gravitational influence on surrounding matter. It is both humbling and beautiful that this first glimpse of what we now call black holes emerged not from complex mathematics or sophisticated instruments, but from the simple, profound act of wondering. Michel's imagination had conjured objects so extreme that they seemed to belong more to poetry than to physics. Stars that had somehow learned to hide their light, cosmic magicians performing the ultimate disappearing act. As we drift deeper into this historical reverie, we encounter another prescient mind, Pierre-Simon Laplace, the great French mathematician and astronomer. Independently arriving at similar conclusions, Laplace wrote of corps obscurs, dark bodies whose gravitational pull would imprison light itself. For a brief moment in his famous treatise on celestial mechanics, he entertained the possibility that the universe might be populated by massive, invisible objects detectable only through their effects on nearby matter and light. Yet this is only the beginning of the story of how humanity began to dream of gravitational prisons for light. These early visionaries were working with the tools of their time, Newtonian gravity, and the corpuscular theory of light, not knowing that they were glimpsing shadows of a deeper reality that would require Einstein's revolutionary understanding of spacetime to fully comprehend. Meanwhile, across the vast expanse of the 19th century, other threads in this cosmic tapestry were being woven. Astronomers were discovering binary star systems where invisible companions betrayed their presence by the orbital dance of their visible partners. They were learning to see the unseen through gravity's subtle choreography, developing the observational skills that would eventually allow us to hunt for black holes in the depths of space. There is something profoundly moving about these first tentative steps toward understanding. Michel and Laplace were like explorers, sketching the coastlines of an undiscovered continent, not knowing that their rough maps would one day guide us to territories even stranger than they had imagined. Their dark stars were simpler creatures than the black holes we know today, objects where light was merely trapped by strong gravity, not regions where space-time itself becomes so curved that the very concepts of inside and outside lose their meaning. As the centuries turned and scientific understanding deepened, these early whispers of invisible giants would transform and evolve, waiting patiently for Einstein's gentle revolution to give them their true form and meaning. In the quiet sanctuary of his study in Berlin, in the year 1915, Albert Einstein was experiencing what he would later describe as the happiest thought of his life. There is something almost mystical about this moment in the history of human understanding, a moment when the nature of gravity, space, and time suddenly revealed themselves to be part of a single, elegant dance. Tonight, as we drift into contemplation of Einstein's gentle revolution, we find ourselves witnesses to perhaps the most beautiful transformation in scientific thinking. For centuries, Newton's gravity had served as a faithful guide to the cosmos, describing an invisible force that reached across space to pull objects together. But Einstein, with his characteristic blend of deep intuition and mathematical precision, began to sense that this was not the complete story. Picture, if you will, Einstein in his famous thought experiment, imagining himself in a windowless elevator. If the elevator were accelerating upward through space, he realized the experience would be indistinguishable from standing in a gravitational field. This simple yet profound insight, the equivalence principle, whispered to him that gravity might not be a force at all, but rather something far more fundamental, the very geometry of spacetime itself. It is both humbling and beautiful that this revolutionary understanding emerged not from complex calculations, but from Einstein's ability to see the universe through the eyes of someone falling freely. He realized that a person in freefall experiences no gravitational force at all. They float weightlessly, following the most natural path through the curved landscape of spacetime. Gravity, in this new vision, became not a pull, but a push. The universe itself, guiding objects along the straightest possible paths through curved geometry. As we settle deeper into this gentle revolution, we discover that Einstein's equations revealed space-time to be a dynamic, responsive medium. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. This poetic relationship, often summarized as matter tells space-time how to curve, and curved space-time tells matter how to move, became the foundation for understanding how extreme concentrations of mass could curve space-time so severely that even light cannot escape. Meanwhile, in the mathematical depths of Einstein's field equations lay hidden the seeds of black hole physics. The equations whispered of solutions where space-time could curl back on itself, creating regions where the future direction points inexorably inward, where time itself becomes so warped that it flows toward a central singularity, like water spiraling down a cosmic drain. There is something profoundly calming about contemplating how Einstein's revolution provided the conceptual foundation for understanding time dilation near massive objects. In his curved space-time, time naturally flows at different rates depending on gravitational potential. A clock runs slower in stronger gravitational fields, not because of some mechanical effect, but because time itself is woven into the fabric of space-time, and that fabric stretches and compresses according to the mass energy it contains. Yet, this is only the beginning of the story that Einstein's equations wanted to tell. They spoke of horizons beyond which information could not return, of singularities where the curvature of space-time becomes infinite, of regions where the familiar concepts of past and future become tangled in ways that still challenge our understanding. Perhaps the most beautiful aspect of Einstein's gentle revolution is how it transformed black holes from Michel's simple dark stars into far more profound and mysterious entities, no longer merely objects that trapped light through strong gravity. They became tears in the fabric of space-time itself, regions where the universe's geometry becomes so extreme that time slows to a crawl and space curves back upon itself in ways that defy visualization, but submit gracefully to mathematical description. In the frozen trenches of the Russian front in the winter of 1916, a German astrophysicist named Karl Schwarzschild was contemplating the curvature of space-time while artillery shells whistled overhead. There is something almost impossibly beautiful about this image. A brilliant mind finding solace in Einstein's equations while surrounded by the chaos of the Great War, seeking cosmic truth in humanity's darkest hour. Picture, if you will, Schwarzschild huddled over his mathematical notebooks by lamplight, his breath visible in the bitter cold, working through the implications of Einstein's newly published field equations. Just months earlier, Einstein had given the world his theory of general relativity, but the equations were so complex that even Einstein himself had been unable to find exact solutions. Yet here, in this unlikely setting, Schwarzschild was about to unlock one of the most profound secrets hidden within those mathematical depths. It is both humbling and extraordinary that the first exact solution to Einstein's field equations emerged not from a comfortable university office, but from the trenches of war. Schwarzschild, driven by an almost mystical devotion to understanding, worked feverishly to solve the equations for the spacetime around a spherically symmetric mass. What he discovered would revolutionize our understanding of how gravity shapes the very fabric of reality. As we drift deeper into this wartime mathematical odyssey, we encounter the breathtaking elegance of what came to be known as the Schwarzschild metric. This mathematical description revealed how space-time curves around a massive spherical object, painting a precise picture of the gravitational landscape in the vicinity of stars and planets. The equations whispered of a critical radius, now called the Schwarzschild radius, where something remarkable and terrible would occur. Meanwhile, within the mathematical poetry of Schwarzschild's solution lay hidden a prediction so extreme that it would take decades to be fully appreciated. At the Schwarzschild radius, the curvature of spacetime would become so severe that time itself would slow to a stop from the perspective of a distant observer. Space would become so warped that the radial direction, the path inward toward the center, would become time-like, meaning that once crossed, this boundary would be as impossible to recross as it would be to travel backward in time. There is something profoundly moving about how Schwarzschild's equations revealed the mathematical architecture of what we now call the event horizon. This was not merely a surface in space, but a boundary in space-time itself, a point of no return where the future direction becomes inexorably inward. The mathematics showed that once matter crossed this threshold, it would continue falling inward, not because of some irresistible force, but because the geometry of space-time itself would allow no other possibility. Yet this is only the beginning of the story that Schwarzschild's wartime calculations wanted to tell. His solution revealed that at the very center of this gravitational maelstrom, the curvature of spacetime would become infinite, a mathematical singularity where the familiar laws of physics would break down completely. Here, in the mathematical heart of his solution, Schwarzschild had stumbled upon what physicists would later call a gravitational singularity, a point where density becomes infinite and the curvature of spacetime becomes so extreme that our current understanding of reality simply ceases to apply. The tragic poetry of this discovery is that Schwarzschild would never live to see its full implications unfold. Within weeks of completing his groundbreaking work, he would succumb to an autoimmune disease contracted in the trenches, leaving behind a mathematical legacy that would reshape our understanding of the universe. His equations, born in the darkness of war, would eventually illuminate the darkest objects in the cosmos. As we contemplate this intersection of human tragedy and cosmic revelation, we find ourselves moved by the dedication of a mind that could find beauty and meaning in mathematical truth, even while surrounded by suffering and chaos. Schwarzschild's solution stands as a testament to the power of human curiosity and the drive to understand, showing us that even in the darkest times, the light of discovery can illuminate profound truths about the nature of existence. There is something profoundly calming about how Schwarzschild's equations continue to guide our understanding more than a century later. Every time we calculate the event horizon of a black hole, every time we model how time slows near a massive object, we are using the mathematical tools he forged in those frozen trenches, connecting our modern understanding to that moment of wartime revelation when space-time first revealed its deepest secrets to human mathematics. In the gentle darkness of space, stars spend most of their lives in a beautiful state of equilibrium, balancing the outward pressure of nuclear fusion against the inward pull of their own gravity. Tonight, as we drift into contemplation of stellar death, we encounter one of the universe's most poetic cycles, how the very forces that give stars life ultimately determine the manner of their death, and in some cases, their transformation into the time-warping giants we call black holes. There is something almost musical about the life cycle of a massive star. For millions or billions of years, these cosmic furnaces burn with steady determination, converting hydrogen into helium, helium into carbon, carbon into heavier elements, climbing the periodic table step by step through the patient alchemy of nuclear fusion. Each fusion reaction releases energy that travels slowly from the star's core to its surface, then rushes out into space as light, carrying with it the story of stellar creation. Picture, if you will, a young Indian astrophysicist named Subramanian Chandrasekhar sailing to England in 1930 at the age of 19, working on calculations that would revolutionize our understanding of stellar evolution. During that long sea voyage, Chandrasekhar was contemplating the fate of white dwarf stars, the dense, hot remnants left behind when smaller stars exhaust their nuclear fuel. What he discovered would earn him a Nobel Prize and reveal one of the universe's most important thresholds. As we settle deeper into this cosmic narrative, we discover that Chandrasekhar's calculations revealed a critical mass limit, approximately 1.4 times the mass of our Sun, above which a white dwarf star cannot exist. This boundary, now called the Chandrasekhar limit, represents a fundamental threshold in the universe's architecture. Below this limit, a dying star can settle into the quiet retirement of a white dwarf, supported by the quantum mechanical pressure of tightly packed electrons. Above it, however, the star faces a more dramatic destiny. Meanwhile, in the hearts of massive stars, those born with more than about 20 or 30 solar masses, an entirely different drama unfolds. These stellar giants burn through their nuclear fuel with profligate intensity, rushing through their life cycles in mere millions of years, rather than the billions enjoyed by smaller stars like our Sun. Their cores become cosmic forges, building increasingly heavy elements until they reach iron, the element that marks the end of the energy-giving fusion process. It is both humbling and beautiful that iron, so common and useful in our everyday lives, represents a kind of stellar death sentence. Iron nuclei are so tightly bound that fusing them requires energy rather than releasing it. When a massive star's core fills with iron, it can no longer support itself through nuclear burning. The delicate balance between gravity and pressure that has sustained the star for millions of years suddenly collapses in a matter of seconds. There is something profoundly dramatic about the moment when a massive star's core implodes. In less time than it takes to blink, the core, larger than the Earth, collapses to a sphere perhaps 20 kilometers across, creating matter so dense that a teaspoon would weigh as much as a mountain. The infalling material rebounds off this incredibly dense core, creating a shock wave that travels outward through the star, ultimately blowing the outer layers into space in a spectacular supernova explosion. Yet this is only the beginning of the story that stellar death wants to tell. For the most massive stars, those that began life with more than about 25 solar masses, even the incredible density of a neutron star cannot provide enough support against gravity's inexorable pull. The core continues to collapse, crushing neutrons themselves until it reaches the point where the curvature of spacetime becomes so extreme that an event horizon forms around the collapsing matter. As we drift deeper into this cosmic transformation, we witness the birth of a black hole, not through some exotic process, but as the natural endpoint of stellar evolution for the universe's most massive stars. The same gravity that once gently held the star together during its billions of years of stable burning now becomes an irresistible force, creating a region of spacetime so curved that time itself slows to a crawl near the event horizon. There is something both tragic and beautiful about how the death of a massive star gives birth to an object that will exist for billions of times longer than the star ever did. While the star burned bright for a few million years, the black hole it becomes will persist virtually forever, slowly evaporating through Hawking radiation over timescales that dwarf the current age of the universe. Perhaps the most poetic aspect of this stellar death cycle is how it connects the microscopic world of quantum mechanics to the grand scale of cosmic architecture. The Pauli exclusion principle that prevents electrons from occupying the same quantum state is what supports white dwarfs, while neutron degeneracy pressure holds up neutron stars. When even these quantum mechanical forces prove insufficient, gravity wins completely, creating the ultimate victory of general relativity over quantum mechanics, at least until we develop a theory of quantum gravity to understand what really happens at the singularity's heart. In the late 1960s, in a crowded auditorium filled with physicists, John Archibald Wheeler was struggling with a linguistic problem that had been quietly plaguing the scientific community for decades. There is something almost comical about the fact that these most dramatic objects in the universe, regions where space-time curves so severely that time itself slows to a crawl, were being described with awkward phrases like gravitationally completely collapsed objects, or frozen stars, or simply collapsar. Picture, if you will, Wheeler at the podium, his mind searching for a term that would capture both the physical reality and the almost mystical nature of these cosmic entities. The year was 1967, and Wheeler, already famous for his contributions to nuclear physics and his work with Einstein on unified field theory, was about to give these mysterious objects a name that would stick for all eternity. In a moment of inspiration, he reached for a term that someone in the audience had suggested: black hole. It is both remarkable and fitting that the name came not from formal scientific deliberation, but from the spontaneous recognition that these objects required language as dramatic as their physics. Black hole captured something essential that the technical terminology had missed: the profound darkness of an object that allows nothing, not even light, to escape its gravitational embrace, and the sense of falling into an inescapable void that the word hole evokes in our imagination. There is something almost musical about how the right name can transform our relationship with a scientific concept. Before Wheeler's christening, these objects existed primarily in the realm of mathematical abstraction, solutions to Einstein's equations that seemed too extreme to exist in the real universe. After 1967, black holes became cosmic characters with personalities, objects that could capture our imagination as well as our scientific curiosity. As we drift deeper into the story of this naming, we discover that Wheeler's choice of words reflected his deep understanding of how language shapes thought. A gravitationally completely collapsed object sounds like a technical malfunction, something that broke, rather than something that represents the universe, operating according to its most fundamental principles. A black hole, by contrast, suggests something mysterious, yet natural, dark, yet magnificent, a cosmic feature rather than a cosmic mistake. Meanwhile, the name began to work its own kind of magic on the scientific imagination. Young physicists who might have been intimidated by discussions of Schwarzschild solutions and event horizons found themselves drawn to the mystery of black holes. The evocative name helped transform these objects from mathematical curiosities into compelling targets for both theoretical investigation and observational searches. Yet, this is only the beginning of the story that Wheeler's linguistic insight wanted to tell. The name black hole carried with it not just scientific accuracy, but also a kind of poetic resonance that would prove prophetic. These objects would indeed prove to be holes in our understanding of physics, places where our current theories reach their limits and new physics must emerge. They would become cosmic laboratories where the deepest questions about information, causality, and the nature of space-time itself would be posed and explored. There is something profoundly beautiful about how Wheeler's naming coincided with the beginning of the golden age of black hole physics. In the late 1960s and early 1970s, physicists like Roy Kerr, Roger Penrose, and Stephen Hawking were developing the mathematical machinery to understand these objects in unprecedented detail. The name black hole gave this burst of theoretical activity a focal point, a way to talk about these discoveries that connected with both scientific precision and human intuition. As we contemplate Wheeler's contribution, we find ourselves moved by his recognition that science is not just about mathematical formalism, but also about the human endeavor to understand and communicate. His choice of name helped transform black holes from abstract solutions to Einstein's equations into objects that could capture public imagination and inspire new generations of physicists to explore the deepest mysteries of space-time. Wheeler, who was also responsible for coining the term wormhole and popularizing the phrase "it from bit," understood that the language we use to describe physical phenomena shapes not only how we think about them, but also how we investigate them. His linguistic gifts helped make black holes accessible to both scientific colleagues and the general public. turning these most extreme objects in the universe into household names. There is something almost prophetic about how perfectly the name has aged. As we've learned more about black holes, that they can spin and merge, that they emit Hawking radiation and participate in the cosmic dance of galaxy formation, the metaphor of a hole in spacetime has proven remarkably robust. These objects continue to be holes in our understanding, places where new physics waits to be discovered, cosmic question marks written in the language of curved spacetime. Perhaps the most beautiful aspect of Wheeler's naming is how it reflects the democratic nature of scientific discovery. The perfect name for these cosmic mysteries came not from a committee of experts, but from the spontaneous recognition shared between speaker and audience that certain phenomena in the universe deserve language as extraordinary as their physics. In the quiet realm of mathematical physics, there exists a relationship so elegant and profound that it reads almost like poetry. Matter tells space-time how to curve, and curved space-time tells matter how to move. Tonight, as we drift into contemplation of this cosmic choreography, we find ourselves witnesses to perhaps the most beautiful partnership in the universe, the intimate dance between mass, energy, space, and time that creates the phenomenon we experience as gravity. Picture, if you will, space-time as a vast, flexible membrane. Though this familiar analogy captures only a shadow of the four-dimensional reality that Einstein's mathematics reveals. When we place matter or energy onto this membrane, it responds by curving, creating valleys and hills in the geometry itself. But unlike the simple rubber sheet analogy we often encounter, real space-time curves in directions we cannot visualize, bending not just through space, but through time as well, creating a landscape where the very flow of temporal experience depends on gravitational potential. There is something almost mystical about how Einstein's field equations, those 10 coupled partial differential equations that relate the curvature of space-time to the energy and momentum of matter, encode this fundamental relationship. On one side of the equations stands the Einstein tensor, a mathematical object that describes the curvature of space-time with exquisite precision. On the other side lies the stress-energy tensor, which captures not just the density of matter, but also its pressure, momentum, and energy flux. The equals sign between them represents one of the most profound insights in the history of human thought, that geometry and physics are one. As we settle deeper into this mathematical reverie, we discover that the curvature of space-time manifests itself in ways both subtle and dramatic. Near a black hole, where the curvature becomes extreme, time itself begins to flow like honey, each second stretching into minutes or hours as measured by distant observers. This is not some mechanical effect or optical illusion. It is the direct consequence of space-time geometry, as fundamental and unavoidable as the fact that the angles of a triangle drawn on a curved surface will not sum to 180 degrees. Meanwhile, the mathematics reveals that matter does not simply sit passively in this curved space-time, but follows what mathematicians call geodesics, the straightest possible paths through the curved geometry. A planet orbiting a star is not being pulled by some mysterious force across empty space. It is simply following the most natural path through the curved space-time created by the star's mass. From the planet's perspective, it is traveling in a perfectly straight line through a curved universe. It is both humbling and beautiful that this mathematical framework explains not just the gentle orbits of planets, but also the extreme behavior near black holes. As matter approaches the event horizon, it follows geodesics that curve inexorably inward until the future direction in space-time points inevitably toward the central singularity. The mathematics shows us that this is not a violent process, but the most natural possible motion through severely curved geometry. There is something profoundly elegant about how the same equations that describe the leisurely orbit of Earth around the Sun also predict the time dilation experienced by matter falling into a black hole. The mathematics makes no distinction between these phenomena. They are simply different manifestations of the same underlying principle, different verses in the same cosmic poem written in the language of differential geometry. Yet this is only the beginning of the story that curved spacetime mathematics wants to tell. The equations reveal that spacetime itself is dynamic, capable of rippling and oscillating like the surface of a pond. These gravitational waves, predicted by Einstein and detected nearly a century later by LIGO, represent spacetime itself in motion, carrying energy and information across the cosmos at the speed of light. When two black holes spiral into each other and merge, they create such violent disturbances in spacetime geometry that we can detect the resulting waves billions of light years away. As we drift deeper into this mathematical landscape, we encounter perhaps the most beautiful aspect of Einstein's geometric vision, its economy of explanation. A single set of field equations explains not just gravity, but also the expansion of the universe, the behavior of time and space near massive objects, the existence of gravitational waves, and the inevitability of black holes. The mathematics reveals that all these phenomena are different aspects of the same geometric reality, the curvature of spacetime responding to the presence of energy and momentum. There is something almost musical about how the Einstein field equations encode the relationship between geometry and physics. Like a vast cosmic symphony, they describe how matter and energy conduct the spacetime orchestra, creating harmonies and crescendos that manifest as everything from the gentle pull of Earth's gravity to the extreme time dilation near black hole event horizons. Perhaps the most profound beauty of this mathematical framework lies in its revelation that gravity is not a force in the traditional sense, but rather the manifestation of spacetime geometry. We do not fall toward the Earth because it pulls us, but because the Earth's mass curves spacetime in such a way that falling is the most natural motion through that curved geometry. Near a black hole, this principle reaches its extreme expression, creating regions where the curvature becomes so severe that time itself becomes geometrically constrained to flow toward the central singularity. In the gentle depths of space, near the gravitational embrace of a black hole, time begins to perform its most beautiful and mysterious dance. Tonight, as we settle into contemplation of gravitational time dilation, we find ourselves witnesses to one of the universe's most profound revelations, that time itself is not the steady, universal metronome we once believed it to be, but rather a flowing river that bends and slows according to the gravitational landscape through which it passes. Picture, if you will, two identical atomic clocks, perfect timekeepers that measure the passage of seconds with extraordinary precision. One clock remains safely on Earth, ticking away in the familiar rhythm of terrestrial time. The other begins a journey toward a black hole, carried by an intrepid explorer who wishes to probe the very boundaries of spacetime itself. As this second clock approaches the event horizon, something remarkable begins to happen. It starts to tick more and more slowly compared to its earthbound twin. There is something almost musical about how this cosmic choreography unfolds. The mathematics of general relativity reveals that time flows at a rate proportional to the square root of what physicists call the redshift factor, a quantity that approaches zero as one nears the Schwarzschild radius. This means that as our brave explorer ventures closer to the black hole's point of no return, each second on their clock stretches into minutes, then hours, then years, as measured by observers watching from afar. It is both humbling and beautiful that this is not some mechanical effect or observational illusion, but rather the fundamental nature of time itself in the presence of strong gravitational fields. Einstein's equations whisper to us that time and space are woven together into a single fabric, and when that fabric curves in response to massive objects, time inevitably stretches and compresses along with the geometry of space. Near a black hole, where this curvature becomes extreme, time learns to move with the patience of geological ages. As we drift deeper into this temporal mystery, we encounter perhaps the most poetic aspect of gravitational time dilation, the phenomenon physicists call gravitational redshift. Light climbing out of a gravitational well loses energy in the process, its photons becoming redder and redder as they struggle against the pull of curved space-time. This redshift is intimately connected to time dilation. The slowing of time in stronger gravitational fields manifests itself in the stretching of electromagnetic radiation, as if the very waves of light are being taught to move in slow motion. Meanwhile, our explorer approaching the black hole experiences something paradoxical and profound. From their own perspective, time flows normally. Their heartbeat maintains its familiar rhythm. Their thoughts proceed at their usual pace. Their instruments tick away seconds in the expected manner. It is only when they look back toward the distant universe that they notice something extraordinary. The cosmos appears to be speeding up around them, racing through time at an accelerating pace as they approach the event horizon. There is something deeply moving about this asymmetry in temporal experience. While the explorer experiences normal time flow during their descent, observers, watching from a safe distance, see them gradually freezing in place, their movements becoming slower and slower until they appear to stop completely at the event horizon. The last photons they emit become so redshifted that they fade into the cosmic microwave background, making the explorer effectively invisible after just a few hours of external time, even though from their perspective, they have already crossed the event horizon and fallen toward the singularity. Yet this is only the beginning of the story that time dilation wants to tell. The mathematics reveals that the effect becomes more and more dramatic as we approach the Schwarzschild radius, following what physicists call a divergent behavior, meaning that the time dilation factor grows without bound as we near the point of no return. At the event horizon itself, time dilation becomes infinite from the perspective of distant observers, creating a temporal boundary as absolute as any physical barrier. As we settle deeper into contemplation of this cosmic slow dance, we discover that time dilation near black holes has profound implications for our understanding of information and causality. If we could somehow retrieve information from near the event horizon, perhaps by sending a probe on a carefully calculated trajectory that brings it close to the boundary but allows it to escape, that information would be extraordinarily redshifted and time dilated, arriving at our detectors like messages from an incredibly slow motion movie of reality. There is something profoundly beautiful about how gravitational time dilation connects the most abstract mathematics of general relativity to tangible, measurable phenomena. GPS satellites orbiting Earth experience time dilation effects that, while tiny compared to those near black holes, are still large enough that they must be corrected for the system to maintain its precision. The same physics that creates the dramatic time affects near event horizons governs the gentle variations in time flow between Earth's surface and the orbits of artificial satellites. Perhaps the most poetic aspect of this cosmic slow dance is how it reveals time to be deeply personal and contextual. There is no universal now that applies throughout the cosmos. Instead, every observer carries their own temporal reference frame, their own version of simultaneity and sequence. Near a black hole, this relativity of time becomes so extreme that the very concepts of before and after become ambiguous when applied to events occurring at different gravitational potentials. The contemplation of time dilation also offers us a profound metaphor for patience and perspective. In our hurried human lives, we often feel that time rushes by too quickly, that there are never enough hours in the day to accomplish all we wish to do. Yet somewhere in the cosmos, near the event horizons of black holes, time moves with infinite patience, stretching moments into eternities, teaching us that the universe itself knows how to slow down and savor each quantum of existence. As we drift toward the close of this temporal reverie, we find ourselves moved by the realization that time dilation represents one of the universe's most elegant demonstrations of the interconnectedness of all things. Space and time, matter and geometry, the local and the cosmic, all are revealed to be aspects of a single, unified reality that responds to mass and energy with the fluid grace of a cosmic ballet performed on the stage of curved spacetime. In the quiet vastness surrounding every black hole lies an invisible boundary that represents perhaps the most profound frontier in all of physics, a boundary not drawn in space but written in the very fabric of time itself. Tonight, as we drift into contemplation of the event horizon, we find ourselves approaching one of the universe's most elegant paradoxes, a surface that exists only in the eye of the beholder, yet marks an absolute point of no return in the geography of spacetime. Picture, if you will, the event horizon not as a physical membrane or barrier, but as a watershed in the flow of time itself. Just as a continental divide determines whether raindrops will flow toward one ocean or another, the event horizon determines whether light rays can escape to the distant universe or must inevitably flow toward the central singularity. This boundary exists at the Schwarzschild radius, that critical distance where the escape velocity equals the speed of light, where space-time curvature becomes so severe that even photons cannot climb out of the gravitational well. There is something almost mystical about the nature of this cosmic boundary. From the perspective of someone falling through the event horizon, nothing special happens at the moment of crossing. No wall is encountered, no sudden jolt is felt, no dramatic change in the local physics occurs. The horizon passes by as smoothly and naturally as crossing an arbitrary line drawn on a map. Yet from the vantage point of distant observers, this crossing represents the ultimate disappearance from the causal structure of the observable universe. As we settle deeper into contemplation of this temporal frontier, we discover that the event horizon embodies one of the most beautiful and disturbing aspects of Einstein's relativity, the fundamental relativity of simultaneity. Events that appear simultaneous to one observer may be separated by vast intervals of time according to another. For someone falling into a black hole, the crossing of the event horizon is a moment in their personal history. For someone watching from afar, this moment is approached asymptotically, but never actually reached. The falling observer appears to slow down and fade away, frozen forever, at the threshold of forever. Meanwhile, the mathematics of general relativity reveals that the event horizon is fundamentally a boundary in the causal structure of spacetime itself. Inside this boundary, all future directed paths lead inexorably inward toward the singularity. It becomes impossible to send signals outward, not because of any physical impediment, but because the geometry of spacetime itself has been so warped that outward ceases to be a direction that leads toward the future. The horizon marks the boundary beyond which the future direction points relentlessly inward. It is both humbling and beautiful that this boundary exists not as a material surface, but as a feature of spacetime geometry itself. The event horizon is coordinatable. It exists at a specific location in space, yet it is also temporal, marking the boundary beyond which events cannot influence the external universe. This duality reflects the fundamental unity of space and time in Einstein's four-dimensional spacetime, where geometric and temporal concepts become inseparably intertwined. There is something profoundly moving about how the event horizon challenges our intuitive notions of boundaries and barriers. We are accustomed to thinking of boundaries as things that can be crossed from either side. We can walk through a doorway in either direction, cross a river in either direction, climb a mountain from either side. The event horizon, by contrast, is a one-way boundary in space-time itself, as absolute and irreversible as the flow of time itself in our everyday experience. Yet this is only the beginning of the story that the event horizon wants to tell. The boundary has profound implications for information theory and the foundations of quantum mechanics. If information falls across the event horizon, can it ever be retrieved? Does it disappear forever from the observable universe, violating fundamental principles of quantum mechanics that suggest information must be conserved? These questions lie at the heart of the black hole information paradox, one of the deepest unsolved problems in theoretical physics. As we drift deeper into the mysteries of this temporal boundary, we encounter the concept of the black hole's stretched horizon, a quantum mechanical refinement of the classical event horizon concept. From this perspective, Information that falls towards a black hole doesn't simply disappear, but rather becomes encoded on the horizon surface itself, stored in correlations between quantum fields that exist at the boundary between the black hole's interior and the external universe. There is something almost poetic about how the event horizon serves as a cosmic membrane between the known and unknowable. Events occurring inside the horizon exist in a realm that is forever cut off from communication with the outside universe, creating what physicists sometimes call the cosmic censorship of singularities. The horizon ensures that the potentially pathological physics of the central singularity cannot influence or contaminate the external spacetime, maintaining the causal order of the broader universe. The contemplation of event horizons also reveals deep connections between gravity, thermodynamics, and information theory. Jacob Bekenstein and Stephen Hawking demonstrated that black holes have entropy proportional to the area of their event horizons, suggesting that the boundary itself carries information about the black hole's internal states. This horizon entropy is enormous. A stellar mass black hole has entropy comparable to all the matter that fell into it, encoded somehow on the two-dimensional surface of the event horizon. Perhaps the most beautiful aspect of the event horizon is how it embodies the tension between the classical and quantum descriptions of nature. Classically, the horizon is simply a boundary in space-time geometry, defined by the condition that light rays can no longer escape. Quantum mechanically, the horizon becomes a dynamic, information-rich surface where virtual particles are promoted to real ones through the Hawking process, where correlations between interior and exterior degrees of freedom are established and maintained. As we approach the close of our contemplation of this temporal boundary, we find ourselves moved by the realization that the event horizon represents one of nature's most elegant solutions to the problem of cosmic censorship. By hiding the potentially troublesome physics of singularities behind absolute causal boundaries, the universe maintains its overall rational structure while allowing for the existence of these extreme gravitational entities. There is something profoundly calming about recognizing that event horizons, despite their reputation as cosmic monsters, actually serve to protect the causal structure of spacetime itself. They are not aberrations or breakdowns in the laws of physics, but rather natural and inevitable consequences of those laws, elegant solutions to the problem of how the universe can contain both extreme gravitational phenomena and reliable causal ordering. In the gravitational embrace of a black hole, matter undergoes one of the universe's most elegantly inevitable transformations, a gentle stretching process that physicists have playfully dubbed spaghettification. Tonight, as we drift into contemplation of this cosmic choreography, we find ourselves witnesses to the delicate interplay between tidal forces and the warping of spacetime, a dance that unfolds with inexorable grace as objects venture too close to regions where gravity's grip becomes overwhelming. Picture, if you will, an astronaut falling feet first toward a black hole, their body extended along the radial direction, pointing toward the center. There is something almost balletic about what happens next. The gravitational force they experience varies with distance. Their feet, being closer to the black hole, feel a stronger pull than their head. This difference in gravitational acceleration creates what physicists call tidal forces, the same phenomenon that causes Earth's oceans to bulge in response to the moon's gravity, but amplified to extraordinary extremes. As our falling astronaut approaches the Schwarzschild radius, this differential stretching becomes increasingly pronounced. Their body begins to elongate, stretching like taffy in the radial direction, while simultaneously being compressed in the directions perpendicular to their fall. The effect is gentle at first, no more dramatic than the mild stretching one might experience while hanging from a pull-up bar, but it grows stronger and stronger as the event horizon approaches, following mathematical laws as precise and predictable as any other aspect of black hole physics. There is something profoundly beautiful about how this stretching process emerges naturally from the curvature of space-time itself. The tidal forces are not some additional exotic physics imposed upon the falling matter, but rather the inevitable consequence of moving through a gravitational field that varies significantly over the dimensions of an extended object. Einstein's equations predict this stretching with mathematical precision, revealing it to be as fundamental and unavoidable as the bending of light around massive objects. It is both fascinating and sobering to realize that the strength of these tidal effects depends dramatically on the mass of the black hole in question. For supermassive black holes, those giants containing millions or billions of solar masses that lurk at the centers of galaxies, the event horizon lies so far from the central singularity that tidal forces remain quite gentle. Even at the point of no return, an astronaut could cross the horizon of such a black hole and survive for hours or even days before the stretching becomes fatal, floating in freefall through curved space-time, while the distant universe appears to accelerate around them due to time dilation. Meanwhile, for stellar mass black holes, those formed from the collapse of individual massive stars, the situation is far more dramatic. The event horizon lies much closer to the central singularity, creating tidal forces so strong that spaghettification would likely prove fatal long before the horizon is reached. The smaller the black hole, the more intense the tidal stretching becomes, following an inverse relationship that demonstrates how the most compact gravitational objects create the most extreme distortions in space-time geometry. As we settle deeper into contemplation of this stretching process, we discover layers of subtle physics that make spaghettification even more remarkable. The differential gravitational acceleration doesn't just stretch objects in one direction. It creates a complex, three-dimensional deformation that elongates matter radially while compressing it in the two directions perpendicular to the fall. Objects become longer and thinner, like cosmic spaghetti noodles, hence the playful terminology that has become standard in the physics literature. There is something almost meditative about how this process unfolds with perfect predictability, following the mathematical choreography encoded in Einstein's field equations. Every atom in the falling object experiences forces that can be calculated with extraordinary precision, creating a stretching pattern that depends on the object's size, orientation, and distance from the black hole's center. The physics is deterministic and elegant, even as the outcome becomes increasingly dramatic. Yet this is only the beginning of the story that spaghettification wants to tell. The process reveals profound insights about the relationship between geometry and physics in curved spacetime. The tidal forces arise not from some mysterious action at a distance, but from the fact that different parts of an extended object follow slightly different geodesics through the curved spacetime near the black hole. Each particle of matter is simply following the straightest possible path through curved geometry, but these paths diverge in ways that create the stretching effect. As we drift deeper into the physics of this cosmic stretching, we encounter the remarkable fact that the falling object itself experiences the process as perfectly natural and inevitable. From the perspective of someone undergoing spaghettification, they are simply floating weightlessly in curved space-time, experiencing no peculiar forces or unusual sensations until the tidal effects become so strong that they overcome the electromagnetic forces holding matter together at the molecular and atomic levels. The contemplation of spaghettification also offers insights into the nature of measurement and observation near black holes. While the stretching process appears dramatic to distant observers who see the falling object elongating and gradually fading due to gravitational redshift, the experience from the falling object's perspective is quite different. Time dilation effects mean that the entire stretching process, which might appear to take hours or days to external observers, unfolds in much shorter, proper time for the falling matter itself. There is something both beautiful and sobering about how spaghettification represents the ultimate triumph of geometry over material structure. No matter how strong the electromagnetic forces holding an object together, whether it's a human body, a spacecraft, or even a neutron star, sufficiently strong tidal forces will eventually overwhelm these binding energies and reduce any extended object to its constituent particles, each following its own geodesic path through the curved space-time near the singularity. Perhaps the most poetic aspect of spaghettification is how it embodies the universe's commitment to mathematical precision, even in its most extreme environments. The stretching follows exact mathematical laws, creating patterns of deformation that can be calculated with arbitrary accuracy using the tools of differential geometry and general relativity. Even in the apparently chaotic violence of tidal disruption, the universe maintains its underlying mathematical harmony. As we approach the close of our contemplation of this gentle stretching, we find ourselves moved by the realization that spaghettification is not a violent or aberrant process, but rather a natural and inevitable consequence of the geometry of curved spacetime. It represents one of the universe's most dramatic demonstrations of how gravity shapes not just the paths of objects through space, but also their internal structure and ultimate fate. There is something profoundly calming about recognizing that even this most extreme process follows predictable mathematical laws, demonstrating that the universe maintains its rational structure even in its most exotic environments. The stretching may be dramatic, but it unfolds according to principles as elegant and comprehensible as any other aspect of physics, revealing beauty and order even in the most extreme gravitational phenomena. In the quiet darkness of his Cambridge study in the early 1970s, Stephen Hawking was contemplating a question that would revolutionize our understanding of black holes and challenge the very foundations of physics. There is something beautifully paradoxical about the discovery that emerged from his calculations. These ultimate gravitational prisons, from which nothing can escape, are actually not completely black at all, but glow with a faint thermal radiation that causes them to slowly evaporate over cosmic timescales that dwarf the age of the universe. Picture, if you will, the quantum vacuum near a black hole's event horizon, that invisible boundary in spacetime that marks the point of no return. According to quantum mechanics, this apparent emptiness is actually alive with activity, filled with virtual particle pairs that spontaneously appear and annihilate each other in fleeting moments shorter than the smallest measurable intervals of time. In the flat spacetime far from any massive objects, these quantum fluctuations have no lasting effect. But near the curved spacetime of a black hole's horizon, something remarkable happens. There is something almost magical about the mechanism that Hawking discovered. When a virtual particle pair appears near the event horizon, the intense curvature of spacetime can separate the partners before they have a chance to annihilate. One particle falls across the horizon, carrying negative energy into the black hole's interior, while the other escapes to infinity as real radiation carrying positive energy away from the system. The black hole loses mass energy equal to the energy of the escaping radiation, causing it to shrink imperceptibly with each such event. As we settle deeper into contemplation of this quantum evaporation process, we discover that Hawking radiation possesses all the characteristics of thermal emission from a perfect black body. The temperature of this radiation is inversely proportional to the black hole's mass. More massive black holes radiate at lower temperatures, while smaller ones glow more intensely. For a stellar mass black hole, the temperature is incredibly tiny, far colder than the cosmic microwave background radiation that pervades the universe, making Hawking radiation essentially undetectable against the thermal glow of space itself. Meanwhile, the mathematics reveals a profound and troubling implication. If black holes evaporate completely through Hawking radiation, and the equations suggest that they must, given enough time, what happens to the information that fell into them during their lifetimes? Quantum mechanics insists that information must be conserved in any physical process, yet general relativity seems to suggest that information falling past the event horizon disappears forever when the black hole eventually evaporates away completely. It is both fascinating and disturbing that this information paradox strikes at the heart of our understanding of physical law. On one side stands quantum mechanics, with its ironclad principle of information conservation, insisting that the microscopic details of any quantum system must be preserved through all physical interactions, even if those details become practically inaccessible through scrambling and entanglement. On the other side stands general relativity, with its elegant geometric description of space-time curvature, suggesting that information falling past an event horizon is forever cut off from causal contact with the external universe. There is something profoundly beautiful about how this paradox has driven theoretical physics to explore entirely new conceptual territories. Physicists have proposed radical solutions, including the idea that black holes might have firewalls at their event horizons, regions of intense energy density that would destroy any information before it could fall into the interior. Others suggest that the information never actually falls inside, but rather becomes encoded in correlations between Hawking radiation and the quantum fields near the horizon, slowly leaking out as the black hole evaporates. Yet this is only the beginning of the story. that Hawking radiation wants to tell. The discovery has profound implications for our understanding of thermodynamics and entropy in gravitational systems. Black holes turn out to have enormous entropy, proportional to the area of their event horizons rather than their volume, suggesting that the information content of a black hole is somehow encoded on its two-dimensional boundary rather than distributed throughout its three-dimensional interior. As we drift deeper into these quantum mysteries, we encounter concepts that challenge our most basic intuitions about space, time, and information. The holographic principle, inspired partly by black hole thermodynamics, suggests that all the information contained within any region of space might be encoded on the boundary of that region. In this view, what we experience as three-dimensional reality might actually be a projection of information stored on a distant two-dimensional surface. The contemplation of Hawking radiation also reveals deep connections between gravity, quantum mechanics, and thermodynamics that suggest a fundamental unity underlying these apparently disparate areas of physics. Black holes obey thermodynamic laws with remarkable precision. They have temperature, entropy, and even satisfy elegant relationships analogous to the laws of classical thermodynamics. This suggests that gravity itself might emerge from more fundamental thermodynamic or information theoretic principles. There is something almost mystical about the timescales involved in black hole evaporation. A stellar mass black hole would take approximately 1067 years to evaporate completely through Hawking radiation, a time so vast that the number cannot be meaningfully comprehended. This is longer than the time it would take for every proton in the observable universe to decay, longer than the time needed for quantum tunneling to rearrange matter into every possible configuration. Yet the mathematics insists that this evaporation is inevitable, that even these most permanent seeming objects in the universe are temporary residents in the cosmic dance. Perhaps the most beautiful aspect of the information paradox is how it has forced physicists to consider the possibility that our current understanding of space-time might be incomplete or emergent rather than fundamental. Some theories suggest that space-time itself might arise from more basic quantum information, theoretic structures, making the apparent conflict between quantum mechanics and general relativity a sign that we need to discover the deeper principles from which both theories emerge. As we approach the close of our contemplation of Hawking radiation, we find ourselves moved by how this discovery demonstrates the profound interconnectedness of quantum mechanics, relativity, and thermodynamics. What began as an investigation of black hole physics has evolved into an investigation of the deepest principles governing information, causality, and the emergence of space-time itself. There is something profoundly humbling about realizing that these darkest objects in the universe have become our brightest guides to understanding the fundamental nature of reality. Through their quantum glow and information paradoxes, black holes continue to teach us that the universe is stranger, more unified, and more beautiful than we ever imagined, revealing connections between seemingly disparate phenomena that hint at deeper truths waiting to be discovered in the quantum geometry of space-time itself. In the quiet, pre-dawn hours of September 14th, 2015, two extraordinary machines, separated by thousands of miles across the American continent, began to vibrate in perfect synchrony. their sensitive instruments detecting ripples in the very fabric of space-time itself. There is something almost mystical about this moment in the history of human discovery. The first time our species directly felt the gravitational heartbeat of the universe, listening to the cosmic symphony that had been playing around us, unheard since the beginning of time. Picture, if you will, the LIGO detectors in their serene isolation, one nestled in the forests of Louisiana, the other in the desert of Washington state. Each facility houses an L-shaped instrument of extraordinary precision, laser interferometers with arms stretching 4 kilometers in length, so sensitive they can detect changes in distance smaller than 1/10,000th the width of a proton. These machines represent perhaps humanity's most ambitious attempt to eavesdrop on the conversations that massive objects conduct through the medium of curved spacetime. There is something beautifully poetic about how these detectors work. Laser light travels back and forth along perpendicular arms, bouncing off mirrors suspended like cosmic wind chimes in the most perfect vacuum chambers ever created on Earth. When a gravitational wave passes through our planet, it stretches space itself in one direction while compressing it in the perpendicular direction, causing infinitesimal changes in the travel time of light that can be measured through the interference patterns of recombined laser beams. As we settle deeper into contemplation of this technological marvel, we discover that what LIGO detected on that September morning was the death song of 2 black holes, each about 30 times more massive than our sun, that had been spiraling around each other for millions of years in a cosmic dance that grew faster and tighter with each orbit. In their final moments, as they merged into a single, more massive black hole, they converted 3 solar masses worth of matter into pure gravitational wave energy in a fraction of a second, a power output that briefly exceeded the combined luminosity of all the stars in the observable universe. Meanwhile, the gravitational waves themselves carried information about their source, encoded in the precise pattern of space-time distortions. The frequency and amplitude of the waves told a story of orbital decay, of 2 massive objects drawing inexorably closer until they merged in a cataclysmic event that shook the fabric of reality itself. Scientists could read in these vibrations the masses of the original black holes, their spins, the distance to the merger, and even details about the final black hole that emerged from their cosmic collision. It is both humbling and extraordinary that these gravitational whispers traveled for over 1 billion years across the expanding universe, carrying their message through intergalactic space while galaxies formed and evolved, while stars were born and died, while life emerged on at least one small planet orbiting an ordinary star. The waves maintained their coherent signal across cosmological distances, arriving at Earth as pristine messengers from one of the most violent events in the universe's recent history. There is something profoundly moving about how LIGO's detection represented the culmination of Einstein's theoretical vision. A century after he first predicted the existence of gravitational waves as ripples in spacetime, human technology had finally become sophisticated enough to detect these subtle distortions in the geometry of reality itself. The discovery validated not just Einstein's specific predictions about gravitational radiation, but also his revolutionary insight that space and time form a dynamic, responsive medium that can carry information across the cosmos. Yet this is only the beginning of the story that gravitational wave astronomy wants to tell. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of additional mergers, creating a new field of multi-messenger astronomy, where gravitational waves complement traditional optical, radio, and X-ray observations. Each detection adds another voice to the cosmic choir, teaching us about populations of black holes we never knew existed and processes we could never observe through electromagnetic radiation alone. As we drift deeper into the implications of these gravitational discoveries, we encounter profound insights about the nature of black hole formation and evolution. The LIGO detections have revealed that stellar mass black holes can be much more massive than astronomers previously expected, suggesting that the physics of stellar evolution and core collapse may be more diverse and complex than our models indicated. The universe appears to be populated by black holes spanning a much wider range of masses than we had anticipated. The contemplation of gravitational wave detection also reveals beautiful connections between the most abstract theoretical physics and the most practical experimental challenges. The successful operation of LIGO required advances in laser technology, vibration isolation, quantum optics, and data analysis that pushed multiple fields to their limits. The detectors must be isolated from every conceivable source of noise, from passing trucks to earthquakes to the quantum fluctuations of light itself. There is something almost musical about how scientists analyze gravitational wave signals, using sophisticated mathematical techniques to extract weak signals from noisy data, like trying to hear a whispered conversation in a crowded room. The process involves creating theoretical templates based on Einstein's equations, then searching through the data for patterns that match these predictions. When a match is found, it represents a direct confirmation that the universe operates according to the principles of general relativity, even in its most extreme environments. Perhaps the most beautiful aspect of LIGO's success is how it has opened an entirely new sensory modality for exploring the cosmos. For all of human history, we have studied the universe through electromagnetic radiation, light in all its forms, from radio waves to gamma rays. Now, we can also listen to the gravitational music of the cosmos, hearing the sounds of black holes merging, neutron stars colliding, and perhaps even echoes from the first moments after the Big Bang itself. As we approach the close of our contemplation of these gravitational whispers, we find ourselves moved by the realization that we live in an era when the universe's most subtle signals have finally become accessible to human instruments. The detection of gravitational waves represents not just a triumph of experimental physics, but also a profound expansion of human sensory experience, allowing us to feel the vibrations of space-time itself and listen to the cosmic symphony that surrounds us. There is something profoundly calming about knowing that the universe is filled with these gravitational whispers, carrying information about the most dramatic events in cosmic history across billions of light years of space and time. Even now, as we contemplate these discoveries in the gentle darkness of night, gravitational waves from distant mergers are passing through our bodies and through the Earth itself, connecting us to the dynamic, ever-changing geometry of space-time that Einstein first envisioned over a century ago. In the early hours of April 10th, 2019, humanity gazed upon the face of a black hole for the first time in our species' history. There is something almost sacred about this moment, the revelation of an image that had lived only in the mathematical imagination for over a century, suddenly appearing as a tangible portrait, a photograph of the invisible, made visible through the patient coordination of telescopes scattered across the entire planet. Picture, if you will, the supermassive black hole at the center of the galaxy M87, located 55 million light years away in the constellation Virgo. This cosmic giant contains the mass of 5 billion suns compressed into a region smaller than our solar system, creating gravitational fields so intense that they bend light into the elegant geometry that the Event Horizon Telescope captured in that historic image. The photograph revealed not darkness, as we might naively expect, but a luminous ring of superheated matter glowing against the profound shadow cast by the event horizon itself. There is something beautifully paradoxical about how we first saw a black hole, not by observing the object itself, which by definition cannot emit light, but by witnessing the shadow it casts against the brilliant backdrop of its accretion disk. The image shows us the photon sphere, that unstable orbital region where light rays can circle the black hole multiple times before either falling inward or escaping to infinity. This glowing ring represents photons that have been bent and focused by the extreme curvature of spacetime, creating a natural lens that magnifies and distorts the light from the hot plasma swirling around the event horizon. As we settle deeper into contemplation of this cosmic portrait, we discover that every feature in the image tells a story about the fundamental physics of curved spacetime. The asymmetry in the ring's brightness, brighter on one side than the other, reveals that the black hole is spinning, dragging spacetime around with it in a process called frame dragging. The side of the accretion disk moving toward us appears brighter due to relativistic beaming effects, while the receding side appears dimmer, creating a cosmic lighthouse effect that encodes information about the black hole's rotation. Meanwhile, the precise size and shape of the shadow provide direct confirmation of Einstein's predictions about the geometry of spacetime around massive objects. The shadow's diameter matches theoretical calculations based on general relativity with remarkable precision, validating our understanding of how gravity warps light paths in the extreme environment near an event horizon. This agreement between theory and observation represents one of the most stringent tests of Einstein's equations ever conducted, probing the behavior of spacetime in gravitational fields billions of times stronger than those we experience on Earth. It is both humbling and extraordinary that creating this image required transforming our entire planet into a single Earth-sized telescope. The Event Horizon Telescope project synchronized radio dishes from Chile to Hawaii, from Spain to the South Pole, using atomic clocks to coordinate observations with precision measured in billionths of a second. The technique, called Very Long Baseline Interferometry, effectively created a virtual telescope with an angular resolution sharp enough to read a newspaper in New York from Paris. There is something profoundly moving about the technical challenges that had to be overcome to capture this image. The project required recording data at rates of several gigabits per second, filling hard drives that were physically transported by jet aircraft to correlation centers, where supercomputers spent months reconstructing the image from petabytes of radio observations. The process involved sophisticated algorithms that could extract coherent signals from the random fluctuations of Earth's atmosphere and the quantum noise inherent in radio detection itself. Yet this is only the beginning of the story that the first black hole image wants to tell. The photograph reveals details about how matter behaves in the extreme environment near an event horizon, where magnetic fields become twisted into complex geometries that accelerate particles to nearly the speed of light. The glowing plasma in the accretion disk reaches temperatures of billions of degrees, hot enough that electrons move at significant fractions of light speed, creating the relativistic effects that shape the appearance of the surrounding light. As we drift deeper into the implications of this cosmic portrait, we encounter insights about how supermassive black holes influence the evolution of galaxies themselves. The M87 black hole powers spectacular jets of particles that extend far beyond the galaxy, shooting material into intergalactic space at velocities approaching the speed of light. These jets, fed by the same accretion processes that create the glowing ring we observe, carry energy equivalent to trillions of stars across distances larger than entire galaxy clusters. The contemplation of this first black hole image also reveals profound connections between observation and theory in modern astrophysics. The photograph serves as a Rosetta Stone for understanding plasma physics, magnetohydrodynamics, and general relativity in their most extreme manifestations. Every pixel in the image encodes information about magnetic field configurations, particle acceleration mechanisms, and the precise geometry of curved spacetime that theoretical physicists are still working to fully decode. There is something almost mystical about how the image captures light that has been bent and twisted by spacetime curvature, creating visual effects that would be impossible to experience anywhere else in the universe. Some of the photons in the image have traveled in complete loops around the black hole before escaping, creating multiple images of the same emitting regions superimposed in complex patterns. The photograph literally shows us light that has been imprisoned in orbital motion around the event horizon before finally breaking free to reach our telescopes. Perhaps the most beautiful aspect of the Event Horizon Telescope's achievement is how it transforms our relationship with these cosmic phenomena. Black holes are no longer purely theoretical constructs or indirect inferences from orbital mechanics, but visible objects that we can photograph and study with the same directness that we observe stars and planets. The image makes tangible what had previously existed only in the mathematical realm, bridging the gap between abstract physics and visual reality. The portrait also serves as a reminder of the incredible journey that light takes to reach us from such extreme environments. Every photon in the image has survived a harrowing escape from the intense gravitational field near the event horizon, carrying information about conditions so extreme that they cannot be reproduced in any laboratory on Earth. These photons have traveled 55 million years across intergalactic space, maintaining their coherent signal through cosmic expansion, galactic motion, and interstellar absorption to finally register in our radio telescopes. As we approach the close of our contemplation of this historic image, we find ourselves moved by the realization that we have witnessed the universe's most extreme gravitational phenomena made visible through human ingenuity and international cooperation. The photograph represents not just a scientific achievement, but also a profound expansion of human vision, allowing us to see objects that exist at the very limits of physical possibility. There is something profoundly calming about knowing that this image exists, that somewhere in our digital archives, we have preserved a portrait of spacetime curvature itself, a photograph of Einstein's equations made manifest in the cosmic laboratory of a supermassive black hole. The image serves as a permanent reminder that the universe continues to reveal its deepest secrets to patient observers, rewarding our curiosity with visions more beautiful and strange than we ever dared imagine. In the quiet halls of theoretical physics, institutes around the world, brilliant minds are wrestling with some of the deepest questions ever posed about the nature of reality itself. Tonight, as we drift into contemplation of the modern mysteries surrounding black holes, we find ourselves at the very frontier of human understanding, where the familiar laws of physics begin to whisper of more fundamental principles that we have yet to fully comprehend. There is something beautifully humbling about how black holes have become cosmic laboratories for exploring the deepest puzzles in theoretical physics. These extreme objects exist at the intersection of general relativity and quantum mechanics, the two great pillars of modern physics that have yet to be fully reconciled into a single, unified description of reality. Near the event horizon of a black hole, both theories make predictions that seem to contradict each other, creating paradoxes that have driven physicists to propose revolutionary new ideas about the nature of space, time, and information. Picture, if you will, the firewall paradox, one of the most disturbing puzzles to emerge from the marriage of black hole physics and quantum information theory. If Hawking radiation carries information out of evaporating black holes, as quantum mechanics seems to require, then the radiation must be correlated with the black hole's interior in ways that create what physicists call monogamous quantum entanglement. Yet this same requirement appears to demand the existence of a firewall of high-energy particles at the event horizon that would incinerate any observer attempting to cross the boundary. As we settle deeper into these quantum mysteries, we encounter the fundamental tension between two seemingly incompatible principles. The equivalence principle of general relativity insists that someone falling through an event horizon should experience nothing unusual. No firewall, no violent disruption, just smooth passage through curved spacetime. Meanwhile, quantum mechanics and the demand for information conservation seem to require that the event horizon be a place of extraordinary quantum complexity, where correlations between interior and exterior degrees of freedom create effects that could be observable to infalling observers. Meanwhile, theoretical physicists are exploring radical solutions that challenge our most basic assumptions about the nature of spacetime itself. The holographic principle suggests that all the information contained within a black hole might be encoded on its two-dimensional event horizon, making the interior volume a kind of projection or emergent phenomenon rather than a fundamental aspect of reality. This idea, inspired partly by black hole thermodynamics, hints that our familiar three-dimensional experience of space might itself be an illusion arising from more fundamental two-dimensional information storage. It is both fascinating and disorienting that these quantum gravity investigations are leading physicists to question whether space-time itself might be emergent rather than fundamental. In some theoretical frameworks, space and time arise from more basic quantum information, theoretic structures, like a smooth liquid emerging from the collective behavior of discrete molecules. Black holes, in this view, become windows into the pixelated or discrete nature of reality at its deepest level, revealing that the continuous space-time of classical physics might be only an approximation valid at macroscopic scales. There is something profoundly beautiful about how string theory, one of the leading candidates for a theory of quantum gravity, transforms our understanding of black holes. In string theory, black holes are not singular points where physics breaks down, but rather complex quantum mechanical objects with internal structure described by the collective behavior of vibrating strings. The theory suggests that information falling into a black hole becomes encoded in the quantum correlations between these stringy degrees of freedom, potentially resolving the information paradox through mechanisms that exist beyond the reach of classical general relativity. Yet, this is only the beginning of the story that modern black hole physics wants to tell. Loop quantum gravity, another approach to unifying relativity and quantum mechanics, suggests that the classical singularity at a black hole center is replaced by a quantum bounce, a region where the extreme curvature of spacetime is regulated by quantum effects, potentially connecting the interior of a black hole to other regions of spacetime through quantum tunneling processes that defy our classical intuition. As we drift deeper into these theoretical frontiers, we encounter concepts that stretch language itself to its breaking point. The ADS-CFT correspondence, one of the most remarkable discoveries in theoretical physics, suggests that certain black holes in curved spacetime are mathematically equivalent to quantum field theories living on the boundary of that spacetime. This duality implies that the physics inside a black hole might be completely described by quantum mechanical processes occurring on the event horizon, providing a concrete realization of the holographic principle. The contemplation of these quantum gravity mysteries also reveals profound connections between black holes and cosmology itself. Some theories suggest that our entire universe might have emerged from the interior of a black hole in a higher dimensional space, making the Big Bang a consequence of quantum gravitational processes occurring at the event horizon of a parent black hole. In this view, black holes become not just endpoints of stellar evolution, but potential birthplaces of new universes, creating a cosmic cycle of creation and destruction that operates across multiple dimensions. There is something almost mystical about how these investigations are revealing unexpected connections between seemingly disparate areas of physics. The mathematics of black hole evaporation turns out to be intimately related to the physics of quantum error correction, the theoretical framework that underlies quantum computing. The quantum information that falls into black holes might be protected and processed by natural quantum error correcting codes encoded in the structure of spacetime itself. Perhaps the most profound aspect of these modern mysteries is how they are forcing physicists to reconsider the nature of reality at its most fundamental level. The investigation of black holes has revealed that our classical notions of space, time, and matter might be emergent phenomena arising from more basic quantum information theoretic processes. In this emerging picture, reality becomes less about objects moving through space and time, and more about information being processed and transformed through quantum correlations. The exploration of quantum gravity near black holes is also revealing deep connections between physics and pure mathematics. The study of black hole entropy has led to discoveries in number theory and algebraic geometry, while investigations of holographic dualities have uncovered profound relationships between quantum field theory and string theory that continue to yield mathematical insights decades after their initial discovery. As we approach the close of our contemplation of these modern mysteries, we find ourselves humbled by the realization that black holes continue to serve as cosmic teachers, revealing the inadequacies of our current understanding while pointing toward deeper truths about the nature of reality. These objects that once seemed like exotic curiosities have become central players in our quest to understand how quantum mechanics and gravity merge into a single, unified description of nature. There is something profoundly calming about recognizing that these mysteries represent not failures of physics, but invitations to discover deeper principles that govern the universe. The puzzles surrounding black holes are guiding us toward a more complete understanding of reality, one that promises to be even more beautiful and surprising than our current theories suggest, revealing connections and symmetries that we are only beginning to glimpse in our theoretical investigations. As we drift toward the close of our gentle exploration of black holes and the nature of time, we find ourselves contemplating one of the most profound questions that these cosmic phenomena pose. What do these extreme gravitational objects teach us about our own place in the vast, curved landscape of spacetime? And how do they illuminate the deeply personal, yet universally shared experience of temporal existence? There is something beautifully humbling about how black holes reveal the fundamental relativity of time itself, the recognition that there is no universal clock ticking away in the background of reality, no cosmic metronome that defines simultaneity for all observers throughout the universe. Instead, time becomes as personal and contextual as a heartbeat flowing at different rates depending on where we stand in the gravitational landscape of spacetime, how fast we move through the cosmos, and which frame of reference we call home. Picture, if you will, our small planet Earth orbiting its ordinary star in a quiet spiral arm of an unremarkable galaxy, yet participating in the same fundamental physics that governs the most extreme objects in the universe. The same principles that cause time to slow to a crawl near black hole event horizons also operate in the gentle gravitational field of our world, creating time dilation effects so subtle that they require atomic clocks to measure, yet real enough that GPS satellites must account for them to maintain their precision. In the contemplation of these temporal truths, we discover that our everyday experience of time, seemingly steady and universal, is actually a local approximation, valid only within the relatively weak gravitational environment of Earth's surface. Venture to different locations in the cosmos, and time itself begins to flow at different rates, stretching and compressing according to the curvature of spacetime created by nearby matter and energy. This revelation transforms our relationship with temporality from something absolute and external into something intimate and contextual. As we settle deeper into this cosmic perspective, we encounter the profound realization that black holes serve as natural meditation teachers about the nature of patience and permanence. While our human lives unfold over decades that feel brief and hurried, these cosmic giants demonstrate timescales that dwarf human comprehension. Stellar mass black holes that will outlive every star in the galaxy, supermassive ones that will persist for trillions of years, slowly evaporating through Hawking radiation across time spans that make the current age of the universe seem like a brief moment. There is something deeply peaceful about recognizing that somewhere in the cosmos, time moves with infinite patience. Near the event horizons of black holes, moments stretch into eternities from the perspective of distant observers, creating regions where the universe learns to savor each quantum of existence with geological calm. This cosmic demonstration of temporal patience offers a gentle counterpoint to our hurried human experience, reminding us that the universe itself knows how to slow down and exist in the eternal present. Meanwhile, our exploration of black holes reveals profound truths about the interconnectedness of all things in the cosmos. These objects are not isolated monsters lurking in the darkness of space, but integral participants in the cosmic dance of galaxy formation and evolution. Supermassive black holes help regulate star formation in galactic centers. Their gravitational influence and energetic outflows shaping the environments where new generations of stars and potentially life can emerge. The contemplation of our place in curved spacetime also illuminates the remarkable fact that we, as conscious observers, represent the universe's attempt to understand itself. The atoms in our bodies were forged in the nuclear furnaces of ancient stars, some of which may have ended their lives by collapsing into the very black holes we now study. We are quite literally made of star stuff that has witnessed billions of years of cosmic evolution, carrying within our physical structure the history of stellar births, deaths, and rebirths that connect us to the deepest processes governing cosmic development. Yet this is only the beginning of the story that our cosmic contemplation wants to tell. Black holes teach us that the boundaries between observer and observed, between the local and the cosmic, between the temporal and the eternal, are far more fluid than our everyday experience suggests. When we measure the time dilation effects near these objects, when we detect their gravitational waves, when we photograph their event horizon shadows, we are participating in a conversation that spans billions of years and vast distances, connecting our brief human consciousness to phenomena of cosmic scope and significance. There is something profoundly moving about how our study of black holes reveals the universe to be far stranger, more beautiful, and more interconnected than our ancestors ever imagined. These objects that seemed like cosmic aberrations have become our teachers about the deepest principles of physics, revealing connections between quantum mechanics and gravity, between information theory and thermodynamics, between the microscopic and the cosmic that suggest an underlying unity to all natural phenomena. The investigation of time dilation near black holes also offers profound insights about the nature of consciousness and experience in a relativistic universe. Our subjective sense of temporal flow, the feeling that time passes, that moments succeed one another, that there is a meaningful distinction between past, present, and future, exists within the broader context of a cosmos where time itself is relative and contextual. We experience temporal becoming within the framework of eternal being, participating in the universe's temporal structure while remaining embedded in its timeless mathematical architecture. Perhaps the most beautiful lesson that black holes teach us about our cosmic context is that we exist at a remarkable intersection of scales and phenomena. We are large enough to contemplate the cosmic and small enough to investigate the quantum, conscious enough to recognize patterns, and creative enough to extend our understanding through mathematics and instrumentation. Our position in the universe allows us to serve as bridges between different scales of reality, translating between the language of human experience and the mathematical poetry of cosmic processes. As we approach the final moments of our gentle exploration, we find ourselves filled with wonder at the recognition that black holes, these ultimate gravitational prisons from which nothing can escape, have actually liberated our understanding of space, time, and our place within the cosmic order. They have shown us that time is not a river flowing past us, but an ocean in which we swim, its currents shaped by the gravitational landscape of matter and energy distributed throughout the universe. There is something profoundly calming about this cosmic perspective. While our individual human lives unfold over brief spans measured in decades, we participate in temporal processes that connect us to the entire history and future evolution of the cosmos. The time dilation effects that operate near black holes operate in gentler forms throughout the universe, reminding us that we exist not as separate observers watching cosmic phenomena from the outside, but as embedded participants in the ongoing temporal symphony of existence itself. In the end, black holes teach us that time, consciousness, and cosmic existence are far more mysterious and beautiful than we ever suspected. They reveal that our brief human experience of temporal flow occurs within a universe where time itself dances to the rhythm of curved space-time, where patience is measured in cosmic epochs, and where every moment of conscious awareness represents the cosmos achieving a fleeting glimpse of its own infinite depths through the temporary arrangements of matter and energy we call human beings.